Just wait a little bit. Let others join. People, just wait for few minutes. Okay, we'll get started as the strength is very low. So just taking little time. Okay. Okay, let's get started. So I waited and more people left. So it doesn't work intuitively. Okay. So first question is about logistic regression. Okay. So we'll revise and understand the theory better first. Okay. So as you can see, so there are two types of classification problem: binary and multi-class. Okay. Um, so nothing much here. Okay. And few example actually, binary classification. Okay, you have to separate these. uh, so what they do is, let me download this one first. This PDF. Okay. How do I draw here? Okay.
Sir, when we will get the solutions of the assignments?
Solution, I think quite late, maybe 1 or 2 weeks later, after the week is done.
Because till now, I we will assume that we will get the solutions of at least two, three assignments.
Haven't got any of that.
No.
Uh, okay. Okay, see what happens. Overall, you're understanding the things, okay?
Yes.
Okay. So let me find a
But
way to
actually,
draw.
for our practice purpose,
Solutions are
we
important. Is the problem without
yes.
solution? What meaning does it have?
Yeah, because actually in the exam also we will expect the same type of question. So if we will practice once, then it will be easy for us in the exam to perform well.
See what type of thing I have to do these days. Okay, let's convert first. Not able to write actually. That's the problem. Okay. Uh, so okay. Huh. So we fit the logistic function. Okay. So as you can see here, so this is going to be the classifier. Okay, W transpose X. Okay, and and as you can see, if it is greater than the probability, if y test is greater than 0.5, they have taken first this type of trying to fit a hyperplane. Okay, but the thing is that um, that is, if there is outlier or any bigger value comes, this will not work out actually. So we use this type of sigmoid function. Okay, and if the probability of this is called logit. Okay, logit is greater than 0.5, then we predict the class 1. Okay, or otherwise class 2. Okay, so that is how we model the classifier. Okay, and let's try to understand more. Okay, and so so it will be something like this. Okay, something like this. Okay. Hmm. And okay, here it is given as well. uh, so as the value is the sigmoid y value, okay, so it is greater than 0.5, we the output it as class 1, otherwise 0. Okay. So let's progress further. You know that similar things. Okay. So theta, so so they have theta defined as this. Okay. So this is a sigmoid function. Okay, and this is our old Bernoulli form. Okay. And so what we are doing is, first we are writing in the form of likelihood. Okay. As you can see, for one sample. Okay, so this is this like this. Okay. And okay, for one sample it is like this, and to write the likelihood you have to product over all the samples, right? So this is our likelihood function. Okay. And so we are calculating the negative likelihood, log likelihood. Okay. So how do we write it? So it is going to be minus, it's a little complicated here, but so we take log of it. Okay. And so it becomes y of, and usually we write theta as g of x. Okay. Means theta term is not used usually, means as a convention. Usually g is used, yi, g, xi, and then it will be 1 minus yi, 1 minus g of xi. So this is the usual loss function. Okay. uh, for uh, for our logistic regression. Okay. Just the negative log likelihood we take as the negative log likelihood, given the likelihood is of the form this. Okay. this this is inspired from the Bernoulli distribution. Okay. As you can see written here as well. Because as you can see, this is like two class problem, right? So it is like a coin toss problem, which class does it belong, it's a head or tail. Okay. So this is our loss function. Okay. You just people keep it in memory and just use it for logistic regression. Okay. The derivation is shown here. Okay. So we'll move quicker. Okay. And so there is another interpretation, that cross entropy point of view. uh, so from the, it is negative, you can take it as a negative log likelihood, or as the cross entropy, which is like the, as you can see, divergence from the reference distribution and estimated distribution. So estimated distribution is our distribution, so this is this one. Okay. Or maybe this one, I can say. Okay, as they have written as well. uh, so these are the ones. Okay. So okay, so this is same as the negative log likelihood. Okay. So as you've got it, mm, so these are some of the things not very robust to outliers. Okay. So outliers, I mean, like so like very high here. Okay. Suppose here, so this will pull the sigmoid like this. Okay. And what will happen, it like the values here will be uh, told as no, because see, they have become less than 0.5. Okay. So not very resistance to outliers. Suppose there is a data point here, so that problem will remain. Okay. And overfitting is there, as in many algorithms. Okay. uh, non-linearity it cannot handle. Okay. Okay. So for non-linear data set, suppose means like you cannot classify it in two half, then you need advanced classifiers. Okay, so this one cannot handle. Okay, so we got the basics, I think. So we can progress into the problems. And mm, okay, so so okay,
Sir,
here
from
is the
that
first.
topic, we can expect from those topics, we can expect only theoretical questions in the exam.
Which topic?
That regression, boosting, and bagging, the topic, these.
Acha, acha.
Hmm.
Yes, means there can be some problems constructed, those simple ones, okay, and are told to solve that one, okay. Means as you can see, the MCQ problems, the questions are easier, okay, but there is also an assignment component here in this course, right?
Hmm.
So if you can see assignment, I mean, then coding work, I mean to say, coding work is there. Uh, Not sure.
Actually, that's why the thing is that we don't have the solutions. So if we want to check the solutions, then how we can check?
Uh, okay, so solutions, okay, but the answer I provide won't be wrong actually. So,
Solutions for our sake, like for our practice, because we
okay,
need to give the exam also.
uh-huh, a reference, right? So you're
Hmm.
making your own solutions that will not work out.
No, currently, we are not making the solutions because previously when we have attended one NPTEL course, so the instructor provides the solutions also.
Acha, no, but solutions will be provided, no problem. But like you should keep your own as well. That's what I'm saying. Okay, let's go to the first problem. Okay, so I, okay, okay. So I do need to tell you more on this as well. Means like the details here are not enough actually. In the slides. Okay. Okay. But let's solve this problem first. Okay. Uh, so what is true about logistic regression? So it is not robust to extreme outliers. Okay. So this is not correct. Okay. It is not suitable for binary classification. That's not correct as well. It does not make any assumption of the data distribution. Okay, so no such assumptions are made. Okay, we take the sigmoid as the non-linearity over our hyperplane classifier. So what I was saying is, uh, this is the one. Let's see. Okay, so okay, so as I was saying, so what I was saying. So we take sigma, suppose G, okay, G of W transpose X. So, what was the point? Actually, I forgot myself. Acha, huh. So we are using this non-linearity. That is the assumption we have, and this is our Y. Okay. So non-linearity is important because, as you can given in this illustration, this means like without a non-linearity, this cannot work out. Okay, because a outlier in that case is like um, deadly. Actually, like it will certainly fail. Okay, so this assumption is non-linearity is sigmoid in this case. Okay, that's a assumption, powerful assumption here. Okay, so that's the only assumption we make here. Others like others all are same. And okay, we'll explain more as well, but let's go through the questions as well. So it requires a large amount of training data. So it does not require a large amount of, but like what does it mean actually? So it's like if you have classifiers like neural networks and like that, so it amount of data used is very high. Okay, but what simple purpose is, the neural networks means this, suppose logistic regression does as well as neural networks. Okay, suppose the complexity is not too high. Okay, and the suppose as binary classification is needed, but any classification problem which is like non-linear, means like suppose this one. Okay, you cannot fit a you cannot separate them using a single straight line, right? So this type of problems you need some non-linear classifiers, because as you can understand, we are using non-linearity here. It's G, that is sigmoid here. Okay, this is sigmoid, but the classifier is still a straight line classifier. Okay, so for example, suppose you have this. The examples in the theory is very less. Okay, so maybe you have not understand it fully, appreciated the importance. Okay, so you have two data set. One is like this is a single data set. This is one class. Suppose someone has cancer. Okay, and so okay, cancer positive. Okay, and this is cancer negative. Okay, so as you can see, and so what are these actually then? uh, what these are the what are these two axes, x1 and x2? Suppose, so x1 can be like the size of the tumor. Okay, size of tumor can be, and suppose this is the it can be maybe age. Okay, age with increasing, means the diagram is not the best, means I should improve, make it more appropriate. So just wait, actually understand better. Okay, so this is age, the size of tumor. So with age and size of tumor, the cancer occurrence should increase, right? So these are the benign case, cancer negative case. Okay, and these are the cancer case. Okay, so you can see that we can fit a straight line to separate these. Okay, so this is our classifier. The equation of this classifier is y is equals to w transpose x. Okay, still w transpose x. So you say the where is the sigmoid gone? Okay, sigmoid is needed. Okay, to just means like why is the non-linearity needed? As you can see, um, means like without the non-linearity, what will happen is like it is similar to a regression problem, right? And okay, so what is this non-linearity helping us? Okay, so it is helping us to decide if the means like the value of this after we means like, as you can see in the place of x, when we are composing. Okay, so we, so the classification y can be here 0 or 1. Okay, so 0 1, so this is w transpose x. Okay, so here g is 1 upon 1 plus e to the power minus x. Okay, so you're getting it. How many students are there now? Okay, 3. Okay, 2. uh, okay, let's continue. So this is our non-linearity. Okay, so as you can understand, this is a composition, right? Composition function. Okay, and so what is happening is that the x is replaced by w transpose x here when the composition happens. Okay, so it is something like this, understand? uh, when w transpose x, okay, uh, okay, for some x1 value, say, okay, or new data point to test whether x1 lies in not x1. Okay, so as you have two parameters here, x1 and x2. Okay, So x1 and x2 you have here. Okay, so this is a new data point. Okay, say 0 here. Okay, 0 represents new data point. Okay, now I need to test whether this person belongs to the cancer group or non-cancer group. Okay, so what can happen actually? Let's see. So if it goes away from this line, okay, so then W transpose X will be greater than 0, right? Okay, so W transpose X is greater than 0. Okay, so as you can understand, this is a increasing function. Sigmoid is like this, right? So as X increases here, okay, the sigmoid value will also increase. Okay, will go to close to 1 as it keeps increasing. Okay, and it increases very quickly, as you can see. Hmm. Clear? So as suppose H transpose X is greater than 0 here. Okay, if the point lies here on the right side, it is greater than 0. Okay, so uh, so as at x equals to 0, as you can see, this is going to become half. Okay, but at more than that, it will very quickly go to 1, and if it less than that, it very quickly goes to 0. Okay, so 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 and and we usually keep a boundary, like if it is less than 0.5, we classify it as 0. If it is more than 0.5, we classify as 1. Okay, so with this non-linearity sigmoid, what we are getting is that we are getting 1 0 form. That is what we need for classification, right? Otherwise you cannot get this one, right? It will be a continuous value. Okay, using this. Okay, and how do we interpret that? Okay, that is a big problem. So for interpretation, why we need 0 and 1, and for that we need sigmoid. Okay, but the classifier, importantly understand, our classifier is still a straight line. Okay, so that is why it is called a linear classifier. Okay, clear? Everyone got it? Okay, only one left now. Wow, serious problem. Ognivo, got it? Hello? 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 No response. Okay, okay, let's continue. So logistic regression is used to predict the probability of a category. So these are the things. Okay, so categorically you can understand, like these are discrete values. Okay, and numerical can be any number. Okay, so yes, logistic regression is for categorical values, 0 1 or 0 1 2 3, like that. Okay, and the 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 value we are trying to predict is dependent on, suppose like y, as I was showing, is dependent on x1 and x2, right? So that is why it is a dependent variable. Okay, so that part is also done. So hypothesis of the logistic regression is between 0 and 1, as you can see from the curve. Okay, this can be between only 0 and 1. Okay, okay, now we are having some strength. So Sukriti, you left, okay, and joined again. Okay, very nice. uh, so so uh, so this has to be so Sukriti, uh, so this logistic regression is an algorithm used to predict the probability of a categorical dependent value, as I explained. So it is like we are trying to predict y, which is dependent on x1 and x2, so it is a dependent variable, and y can take discrete values like this, so that is why it is categorical. Okay, so and the hypothesis of the logistic function is between limit 0 and 1, so it's very simple to see as well, because our hypothesis is g of w transpose x, and g's range is 0 to 1. Okay, so our hypothesis will have range 0 to 1. Okay, simple, right? Any doubt up to this? So one question for you guys, Sukriti and Ognivo, uh, like if we are using non-linearity sigmoid in logistic regression, why is it still called a linear classifier? Hello, anybody? Anybody know answers? uh, okay, so as I explained, the classifier is still linear. Okay, we are using the non-linearity to classify it between 0 and 1. Okay, not between 0 and 1 only. Okay, so that's the idea. Okay, so let's continue actually. So it is one strange question only. um, so let me explain. uh, okay, so this is it. Oh, okay, so let's try to understand this problem. Okay, so first, log of odds. Okay, uh, so first to define odds actually. Okay, so odds of happening, what does it mean? It is the probability of happening, okay, divided by 1 minus probability of happening, means probability of not happening. Okay, so this is called the, means the desired class that we need to happen. Okay, is p, and 1 minus p is the undesirable class. Okay, so it is the division of these two. This is called odds. Okay, so, going on, so we are given minus 64 into 2 hours. Okay, So now what we'll do is you take hour as 34 as given in the problem. 34. Okay. So this is our p over e to the power 4. Okay. So e to the power 4 equals to p over 1 minus p. Okay. So to find the odds, you take the anti-log as well. Okay. So this is it. Okay. Okay. So now let's go next. So p upon 1 minus p is equals to e to the power 4. Okay. So you need to find p from here. You can do the multiply and separate the variables. Okay. But in this situation, what I do comfortably is dividend. Okay. So I just add it. Okay. So I need to add e to the power 4 in the denominator. Okay. So we get p. Okay. So clear up to this. Okay. Clear. No response. Okay. Okay. Let's continue. Hmm. Okay. So let's continue. So this is our probability. Okay. So this is what we needed actually. Uh, so you calculate it. It comes out to be about this one. Okay. This is the answer. Clear. Very simple problem. Nothing is there. But the table is useless as well. So strange problem. We're already given the classifier. Okay. So we don't need to train it or anything. Okay. Clear. Clear, right? Okay. So let's continue. Next question is on decision trees actually. So I'll explain the decision tree part a little more. I mean, not discussed at all now. So we're going to get started with decision trees uh, from the notes here. Okay, so this is the one. So first, let me convert to a what do you call that PowerPoint so that I can write on that. Okay. So this is another type of classifier. Okay, more complicated. Okay, and so more powerful one as well. Okay. So and it is not linear for sure. Okay. as you can see, this case that we were not able to solve with linear classifier like logistic regression, they have been able to classify with this decision tree. So if we get into it, okay, uh, so so as you can see, a possible decision tree for the data. So first we take one attribute, okay. So we take one attribute, let's say outlook here, okay, and we're classifying on that sunny, overcast, and rain, okay. And Hmm. So we keep doing this until we get to the classification that is yes or no. Okay. So actually the problem is in the later part actually. So maybe a little harder to relate here. So so this is like yes or no. Here is the play tennis or not. Okay. So this is the part we're trying to classify. Do we need to play tennis given the situation, or do we not play tennis? Okay. So but the situation, as you see, is much more complicated. Okay. Than previously. Okay. Okay. Uh, so let's continue. Okay. So as you, this diagram will be very important here. Okay. So as you can see, they have its decision tree classifies the region into in like super rectangle. Okay, so that is what they mean to say. So it is quite important to understand the rectangle. Okay, quickly we will do here. Okay, no problem. Anyway, the questions are simple. Okay, so so first we start with x2 here. So this is this one. So if it is less than 3, okay, so this is the one less than 3, this region, okay. And as you can see, x1 is less than 4, so this square is the one, okay. First we get that, okay. So this denotes a 0, so we replace with 0, okay. Next, if x1 is greater than 4, okay, so this one, okay, so this region is 1, as you can see, this one, okay. So are you able to interpret? Okay. So x1 is less than 3, then x2 is less than 3, and x1 is less than 3. Okay, so this is the one, I think. X2 is less than 3, x1 is less than, I think it's already I mean, some sub cases are here. So so then we have x2 is greater than 4, okay. So 4 is this one, so I forgot actually. Let's see. So x2 is less than 3 here, okay, so this is the one. And then we have x1 less than 3, okay, okay. So this is the one, okay. Then after that we have x2 is less than 4. What they're doing is x1 is less than 3, then two cases, okay. Okay, acha, this is the line, okay. So this is already 0, x2 is less than 4. Acha, x2 is less than 4, then 0, uh, then 0, and x2 is greater than 4, then in this situation is 1, so this box, okay. And I think this is the one they call as this situation, yes. So yes, it is actually, as you can see, x2 is less than 3, okay. So below this, x1 is less than 3, so this, okay. uh, so otherwise I think still not fitting very well, okay, but okay. So these are the type of we have, okay. So the problem we are unable to solve with logistic regression because it is a linear classifier. We are able to solve here, okay. So if we prepare the tree as well, okay. So first we see a here, okay, a true or false, okay. So if it is false, we go to B, false or true. Okay, so false and true situation, true, true and false situation, true, otherwise false. Okay, so this is the type of classifier. Okay, okay, so okay, like this. Next, as you can see, classification, regression, both problems can be solved. So this is discrete problem, or this is the problem we are going to analyze very well. Okay, so this is a continuous problem. As you can see, x1 and x2 are continuous problems. Okay, because we are taking all the values in between. Okay, and we have mixed problems can be also there. So not much details will go here. And so regressions, as you can see, regression can be solved as well. Uh, so so as you can see, so they have defined these values. Okay, okay, so different values represent different okay, so but as you can understand, to have good inference on regression, we need a larger decision tree. Okay, because some area is there, like, which is very empty. And so what will it be? Will it be in will it be this value or that value? It's hard to predict if we have less number of classes here. Okay, it's not classes, I mean the y values, truth values. Okay, so not very hard here. Okay, uh, so we use a greedy approach here. Okay, uh, hope you're enjoying. Maybe so we use a greedy approach here. Okay, and so first is to see that we are okay, so the idea is like here. Okay, so we take the help from information theory. Okay, this entropy. Okay, so the idea is like this. Okay, as you can go here, so we find the mutual information. Okay, correct here. Yeah, yes, so mutual information we find. Okay, I x comma y. Okay, it is also called information gain. Okay, so for any parameter in which the mutual information or information gain is the highest, we first use that to classify the decision, to start the decision tree, to build the decision tree. Okay, to, or you can say that, to grow the decision tree. Okay, so let's focus on this. Okay, uh, so we start with two examples, coin flipping actually. So two scenario actually. So in this scenario, you are having two head and 16 tails. Okay, so this ratio we have got. Okay, and in sequence, two, as you can see, 8 and 10. Okay, okay, so we find the entropy here as well. So it is a important step in towards the calculation of information gain. Okay, so how do you find the entropy here? So this ratio, this is for the tail, right? So this ratio, or you can say the probability of, means trial probability of it, occurrence of a tail. Okay, into log of that. Okay, and so this is what we get. Okay, probability of occurrence. Okay, and log of that. Okay, so this is what we call the for means entropy. Okay, okay, so this is what we call entropy. So we calculated entropy for both of these. Okay, 0.5 and 0.99. Okay, so so we are understanding this is better as well. So like entropy we have, and the probability p of heads. Okay, so I'm going little fast because I think you understand these things little bit as well. Okay, uh, do you understand this thing, or maybe I can go slower as well? Anybody? Okay, 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 let's continue. Okay, so as you can see, the entropy, as you can see, is maximum when the probability of occurrence is 0 0.5, okay, otherwise it is below that, okay. So as you can see, it is close, okay, so it is very close to 1. It is close to, as you can see, 0 0.5 here. Okay, ratio is close to 0 0.5, okay. So the entropy is maximum, okay. Okay, so what does it mean first, okay, little bit of information theory, okay, it's very important to understand, okay. So what does high entropy mean, okay, what does it represent? So variable has a uniform like distribution, okay, that the probability becomes same, okay. So it is like a uniform distribution, of flat histogram, as you can see, like a flat, okay. So it is less predictable as well, okay. Means what happens is that means like you cannot tell whether it is a head or tail if they're so close, okay. So has many peaks and valleys, okay. So it is very easy to understand. So we calculate information gain, okay. So we got the entropy here, okay, and specific conditional entropy is also there, relative entropy that is called, okay. So important to understand this one better, okay. uh, so then we'll be able to solve the problems, okay. So this is the relative entropy, okay. So we'll take an example to understand, okay. So the example is this one only, okay. So wait a minute. hmm. Okay, so we'll go like this, okay. um, so the idea is something like this, okay. So let me explain. So should take the example simultaneously, so it will be easier to understand, okay. So this is our example, okay. So the outlook, as you can see, outlook means the weather outlook. What can be? Sunny, overcast, rain, like that. Temperature, hot, mild, cool, okay, like that. Humidity, so means like these are the parameters, the x values, okay. So this x1, you can say x2, x3, okay, like that. And this is our y value. So total we have 4 x values, okay, 4 parameters on which y depends, okay. And so if you take the example, okay, so first we're calculating the entropy S, okay. So as you can see, so how did we calculate the entropy? If you can remember, what we are doing is what, like take the positive values, okay, is our play tennis is the yes is the positive values, okay. Then take the ratio of that, okay, and like that, okay. You got this one, right? So easy. Um, so that is how we got the entropy as given in the formula as well here, okay. So the idea means like if you interpret, if you want to understand this formula, okay, maybe you can be a little bit more interactive. Hi, V Sai Likita Vinotini K, anybody? No. Okay, it is quite strange actually. uh, okay, so let's continue. So what does it mean actually, like for every x values, okay, okay, we are summing up this entropy, summing of this whatever expression, okay, px equals to I, and like that, okay. So what I mean to say is, so in this calculation what you're doing is, for every uh, means like sunny. Okay, so x is equals to I. What this means? X is x1. Okay, so x1 is sunny. Okay, so for sunny, what is the probability? That will be uh, okay. So what will be sunny is like 4 5 5. Okay, so 5 funny 5 is there. Okay, of occurrence. Okay, so we will take yes and no like that. Okay, it's like what the idea is, like even with this formula it condenses to exactly this. Okay, that so this is the expression for entropy. Okay, so and these three are the conditional entropy or relative entropy. Okay, so how do we find that? Okay, so let me explain. So as you can see, the conditional entropy is defined as for class V. Okay, means the our final class, that is, do we play or do we not play? Okay, so suppose we play. Okay, so for each class. Okay, uh, okay, do we play or play not? So we find this entropy. Okay, relatively. Okay, so given this class happens. Okay, so this is our conditional entropy. Okay, okay, so let's continue. So as you can see, if when there is sunny here. Okay, so there are five sunny values, I think. Five sunny values. So here we have how many yeses? uh, one, two yeses. Okay, so that is what they've written. Okay, and three false. Okay, three no. So for that we have written it. Okay, so in terms of 5 and 2, so we have written it, and with the entropy we get it 0.971. Okay, so we'll take a little break here actually. Then we'll join back. Okay, 5 minutes break. Okay, and then we'll get started again. Okay, so be here. Okay, it'll be quick. Sorry everyone, got a little bit more late, 5 minutes late. Okay, so let's get started again. Okay, so the entropy part is entropy, or what do you call that? Conditional entropy is clear, right? And now we are trying to find the gain. Okay, information gain. Okay. Hmm. So we have done up to this part. Okay, so the gain is defined as, or mutual information of x and y is defined as this entropy of x. Okay, so this is that total entropy. Okay, and another is x given y, or entropy of y, so like that. Okay, so this is entropy of s, as you can see, and like that. Okay, so so just need to have some bigger. Okay, so you're summing over this, and this is the sv by s. So how do we define that? Sunny total number of examples is 14, as you can see, or examples. Okay, and out of that the 5 is the in which it is sunny. Okay, so you take it like that, so you can calculate the gain. And so this is gain for s outlook. Okay, hmm. So as you can see, we have s sunny. Okay, which is part of the outlook. Okay, overcast and rain. Okay, so you got this one. Okay, for the outlook one. Okay, so information gain with respect to outlook, as you can see, is this one. Okay, so similarly we have to find for other parameters as well: temperature, humidity, wind. Okay, so this has to be stated after that. So as you can see, so wind, humidity. Okay, wind, humidity, temperature should be here. Okay, so these are the value of the information gain we get. Okay, so how does it help us? Okay, so as I said, this will help us decide which one to take first. Okay, so as you can see, the outlook has the highest information gain. Am I correct? Right, so outlook has the highest information gain. Okay, so you take outlook, there are three sub classifications: sunny, overcast, rain. Okay, so you get there. Okay, next most important is, as you can see, humidity. Okay, so humidity is most important next. Hmm. Okay, in sunny, as you can see, these are the days we have. Okay, so that's it, like +2 -3, as you can see. Okay, like that. And very interesting thing, as you can see, just after one classification we are able to classify this overcast. Okay, because in overcast all are yes. Okay, so we have already reached a classification. Means, like, what does it mean? If we are given a overcast condition, okay, so it means play tennis. Okay, that is how we have already got it. Okay, so next what we have is here. Okay, so next, but we have to classify these two, right? So we go to the next, which has the most highest information gain. That is Okay, where is it gone? Mm, okay, so next highest is humidity. Okay, so we'll classify next with humidity. That is high, normal. Okay, so high and normal is there. So we need to classify with respect to humidity next. So where is it? Okay, what have they done here? Acha. So that as you can see, we are trying to sub-classify, right? And subclass after the classification with respect to this uh, outlook, we are trying to classify with respect to each of these three. Okay, okay. So what we'll do is that we will do with this values only. Means this we will do the same calculation with these with this sub table. Okay. So from that we'll get three information gain again. Okay. So in this we get three information gain here. Let's see. So these are the three information gains. So the highest is 0.97. Okay, humidity. So we need to do with respect to humidity here. Okay. Uh, okay. So we are doing with respect to humidity here. Okay. So next the rain, whatever is there. Okay. So we need to do that as well. Okay. So they will take another sub table. Okay. Okay, so like that you can do it. Okay, as soon as you reach a class which is like uh, classified, okay, well classified, then you don't need to proceed further. That is the end. Okay. So something actually, uh, we'll soon go to the problem. Just have some patience. Okay, almost done. You understood everything, I think. Uh, so So how can you stop overfitting? Actually, overfitting as long as the um, this graph or tree, you can say, keeps growing, it can lead to overfitting. Okay. So another class. This is a classical solution that is having more training data. Remove irrelevant features is also classical solution. You'll find that in every method. Okay. So these are the ones. Stop growing tree when the data. So if it reaches statistical insignificance, okay, means like suppose it is providing 95% accuracy. So don't need to do it. Don't need to grow the tree. Okay. So this is the advanced topic. Okay, we'll not cover this. Okay. Uh, Post prune. Okay. Okay. So how do we have some best tree? Okay. So okay, so that was one thing. So Gini indexes we use for in the case of classification to uh, see whether the our what do you call that decision tree is good or not. Okay, and it is a much faster criterion, less computational expensive. Okay, but results of entropy criterion is slightly better. Okay, so for in the case of regression we need mean squared error. Okay, so next what we have here is that okay, so these are not considered in the syllabus. Okay, so let's go to the problems quickly. uh, hmm. so so this is the question. Okay, So and so how do you quality of split, how do you determine that? So we have, so let me make a slide as well, slide out of this. So as you can see, so these are all the three required, okay, as we have studied already, okay. Gini index, okay, and intro information gain, we exactly use it, okay, to 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 do the split, okay. So it is very important. Entropy is like the precursor to information gain, okay. So all of this is important, okay. So this is the answer, question number 5. Next what we have is, okay, okay, let's continue. So this is a good problem actually, you can understand, similar to the one we have done, okay. um, but a short problem actually. We need to find the information gain here. Okay, so we'll continue with that. Okay, so we have six instances in that previous case. So we had 14. So classification is the y values, and a1 and a2 are the parameters, okay. So first what we need to do is the find the total entropy, okay. What will be the total entropy here? So let's denote total entropy by S, okay. So what will it be? It is minus of, okay, minus of our good, our desirable class, that is plus, that is 3, okay, divided by 6 log of 3 by 6. Okay, and undesirable class is this minus 1, so that is also 3, okay. So as you can understand, this will be let's see, any mistake we have done? No, no mistake, okay. So this is our total entropy, okay. So it has to be 1 actually, but let's see the calculation, okay, because if it is 50-50, the answer has to be 1, okay. So as you can see, 2 times repeated, okay. So we'll not write this one, just make it 2 times. So minus log of half, okay. So it becomes, so we take it base 2, okay. So it becomes 1, okay. Okay, so we are done with this, okay. So next we need to find the entropy with respect to, okay. So if we see the examples, okay, see our previous example, we'll compare with that to help understand better. What is it? Okay, so first what we did, hmm. so so let's do it, okay. So So first we take the one parameter, that is outlook, okay, and we classify, we find entropy with respect to each of this, okay. Okay, so only a1 is required, okay, so a2 we can ignore, okay. So first we've got s is equals to 1, the total entropy. Next what we need to do is just the same exercise, okay. So let me show you, okay. So first for true, okay, in case of a1 we are looking for, okay, so cannot forget this one, okay, we're looking only on a1. And if you compare with this example, okay, that is this one, okay. So what we need to this entropy of true and false, right? So these are two classes in our problem. Here sunny, overcast, rain, but in our problem it is two classes, okay, true and false, okay. So s, let's write it better. So entropy, this is conditional entropy, s true, okay, and conditional entropy s false, okay. Okay, so this is what we need to find, okay. So when it is true, how many times it's true? 3 times, right? So it should be minus 3 first, okay. And out of that, how many times we have classified it positively? Okay, so that is 2 times. So this is 2 log, same repeated, 2 by 3, then minus 1 by 3, then log of 1 by 3. So this comes out to be about 0.9183, okay. So I've calculated before, so this comes out to be this, okay. In the false case, what we have here is that there are 3 false, okay. So this becomes 3, and how many plus is 1, okay. This is 1 log of 1 by 3. Next is minus 2 by 3 log of 2 by 3. So this comes out to be, okay, actually same, okay, just the terms are reversed, 0.9183. So this two conditional entropy are same, okay. Next what we need to do is mm. So next what we need to do is we need to find the information gain, okay. So that is equals to, okay, we'll go to our previous slide, okay. So as you can see, information gain is the total entropy minus the conditional one, okay. But in that ratio is important, okay. Let me show you. So what we have is here, so the total number of true false values is 6, but out of that 3 is true, and the our yeah, this is for entropy 0.913, 0.9183, 9183, then minus 3 by 6, 0.9183. So this comes out to be 0.0817. So this is our answer, okay. So that is what we have to done, right, do, right. As you can see, uh, here if you look, this ratio is important. How many total samples? That is 6 in our case, and how many these true samples, okay. So that is our 3 in our case, okay. That is what I have used, this ratio, 3 by 6, 3 by 6, okay. Okay, so this is how our problem is solved. 0.817 is the answer. So let's mark this, okay. Next, so how is pruning used to prevent overfitting in decision trees? So So option B is the best answer, as you can see, going on by our theory. So we were so so we were removing, means we were adding branches with the highest information gain. Okay, so we'll not add branches with low information gain. Okay, so that is how our answer is option B. Very simple, right? Limiting the depth is correct, but it is not exact to the point. Okay. Others are wrong. Limiting the these are wrong. Okay, absolutely wrong. So this is part of the theory actually. Is temporal model. Okay, is hidden Markov model. Okay, it's part of the theory. I can go through that as well, but I will prefer if we do the hidden Markov theory in the next class. Okay, but so this two are covered. Okay, okay. So cover this hidden Markov model 3 questions. We'll cover in the next class. Okay, and so so this is how we close. Okay, okay. So we're finishing now. Okay, uh, and okay. So we will have the week next week, week 6. Along with that, we'll do the hidden Markov model. Okay. Okay. Thank you very much.